Did you know that among US adults aged 65 and older, 1 in 9 people suffer from Alzheimer's dementia? And not only that, scientists have predicted that as life expectancy increases by the year 2050, more than 100 million people will suffer from Alzheimer's disease. To put it in perspective, that's more than a fourth of the US population. These are really scary numbers, especially if you consider the fact that Alzheimer's is an irreversible, progressive disease that has no known cure yet. Scientists have been working tirelessly to try to find a cure for this disease. However, before we get around to finding a cure, we need to figure out what causes Alzheimer's in the first place. Now, Alzheimer's is a brain disease, which means that we have to look to the brains of patients with Alzheimer's to try to figure out what's really going on. If you look at this picture of a healthy brain versus this picture of the brain of a patient with Alzheimer's, you can see the formation of these aggregates or clumps of proteins that are known as plaques. Now, you might have heard of plaques as your dentist mentioning that plaques are bad for your teeth. Similarly, plaques in your brain are bad for your brain, and the formation of these plaques or the clumping of these proteins is what is causing Alzheimer's in the brains of these patients. But how do we get from here to here? What causes the clumping of these proteins? This is precisely what I'm trying to figure out with my research. I study the clumping of proteins in vitro, which simply means that I take these proteins in a test tube and then I try to mimic the conditions that it sees in the brain to try to figure out what sort of chemical imbalances causes clumping of proteins. I do that using visual as well as advanced microscopy techniques that help me identify the formation of these clumps. Understanding why these proteins clump together is the first step towards finding a cure for Alzheimer's disease and improving the lives of more than 100 million people in this world. Thank you.
16 years ago, one of the worst air disasters in my home country, Nigeria, dampened the joy of Christmas. Soliso Airline, conveying mainly high school students traveling from the capital city, Abuja, for the Christmas holidays, crash landed. Only 2 out of the 110 passengers on board survived. This crash, as investigations revealed, was due to a combination of poor pilot performance and low visibility conditions. Unfortunately, low visibility still remains a critical factor affecting safety in worldwide aviation operations. Although new technologies are coming in, such as the enhanced flight vision systems, or EFVS for short, it is unclear on how this technology will disrupt or change the pilot's visual scan and consequently how they control the aircraft. The primary objective of my research is to build a model that provides insights on how the pilot's visual scan and control behavior is impacted by the EFVS. The use of EFVS has raised several human factor issues. With the model, it was discovered that the use of EFVS led to inconsistencies in the pilot's visual scan that affected his control activity and led to poor pilot performance. Imagine a scenario where the issues associated with low visibility for the pilot were not only solved, but the human performance issues associated with the use of EFVS were understood and addressed. A model that learns to identify the inconsistencies in the pilot's visual scan during the use of the EFVS can assist cockpit designers in making engineering design decisions, as well as the FAA in safety and design certifications. Once again, my name is KAOSI, and my goal is to make aviation safer. Thank you.
Did you know that the first computers took up an entire room? Now we have computers that fit in our palms and on our wrists. But how have computers been able to get so small? The answer is silicon transistors. Silicon transistors are the parts that make up computers. Nowadays, silicon transistors are so small that they're able to fit on the tip of your finger, but there's still one major downfall. Silicon is a brittle material, and this means that the silicon transistors can crack easily during manufacturing. So how are we able to detect these super small cracks in the transistors? This is where my research comes in. We use ultrasound to detect cracks in super small silicon wafers, which are used to create transistors. The technologies that we use can be thought of like the ultrasound medical device of fracture sonography. When you break a bone, you're able to not often see the crack from the outside of the bone. And instead, when you go into the doctor's office, they scan over your body, create an image, and are able to detect the crack. We use similar technology, but instead of scanning over bones, we scan over silicon wafers. Now, we're not only interested in detecting the crack, but we're also interested in sizing the crack. In order to size a crack, we're able to use wave scattering. Wave scattering can be thought of as light scattering. If you have a piece of glass with a crack in it, light goes in, bounces around, and comes out in a bunch of different directions and has different colors. We're able to rely on similar techniques to measure cracks in silicon wafers. Using this research, we have been able to detect previously undetectable cracks in silicon samples. Crack detection is going to become increasingly important as technology advances and computers reduce in size. Using our research, we will be able to improve the quality of semiconductor transistors and continue the technological revolution. Thank you.